Hello and welcome to a new Thinking Particles tutorial video. I'm your host Edwin Braun, and in the next 30 minutes I will show you how to turn objects into dust on contact with another object. This is an unscripted tutorial recorded live. Simulation rendering and screen recording is done on the same machine. Let's start with the scene. The scene is pretty simple. It has a few objects, pyramid, spheres and torus, and the bowl. And that's all. We throw the objects into the bowl. Let me bring up the user interface now of Thinking Particles. So let me select Thinking Particles, click the properties, and we'll get our Thinking Particles user interface. First, let's have a look at the particle groups. We have several particle groups and subgroups, and the force is one to note. Everything underneath force will receive gravity, so the objects and our sand simulation will receive gravity. Then we have also a tracer group, but we are not caring about that right now in this tutorial. Let's go to the dynamic sets. The create dynamic set is responsible for bringing in our main object, the sphere, the pyramid, another sphere, and the torus. Each of the newly created particles will get their properties assigned. One important property is the BT rigid body dynamics property, so that will allow us to have rigid body collisions, for example. Then we have the mass and the memory operator, which is a very special case here. What we want to achieve is we want to remember which object is which later on. So we want to know which is the sphere, pyramids, torus, and so on. So we are using the memory operator to store in an integer our born node ID. So when the object-to-particle creates a particle out of our 3D Studio Max objects, it also gives us a number. And that starts with 0, 1, 2, 3. We will need to use these object ID later on, and I will go into detail in explaining it. Let's move on to the next dynamic set, and this is our force dynamic set. We are using the include sub-object groups option, which means all particle groups underneath force will receive the gravity. Let's move on to the next dynamic set. The NPM dynamic set handles the sand simulation and the creation of our sand particles. It's a pretty complex dynamic set, and we'll go through step by step what we did here. The first thing is our flow NPM node. There we set which particles should be affected by our NPM solver and what type of solver we choose, and the type is set to sand. I'm not going to discuss how we did the setup of the sand solver. Let's go to the flow boundary. Which is much more interesting, because in the flow boundary I just picked a low resolution version of our bowl. And I want to have that because for our sand simulation I want to have the collision with a lower resolution object. Let me just show you the low resolution bowl, and it has less subdivisions. It's a more rough representation of our bowl, but all the curves are there, so that's pretty good for our purpose right now. Let me just bring back our rendering resolution, the higher resolution bowl, where you can see we have much more subdivisions, and we use that just for the rendering only. Internally, we use with the flow boundary our low resolution object. So every collision will be done with the lower resolution. The next flow boundary we have here is our object. So I want to have a collision with our objects as well. So the sand should interact with any geometry that might be left over or drop into the sand. And I also have a third flow boundary, and that's called kill box, that will kill sand particles on impact with the kill box object. It's always a good idea to have something like that in your scene when you're doing particle simulations. Stray particles that will fall out of the bowl will be automatically killed when they hit this kill box area. So everything that strays or falls out there and drops down will be killed on impact. That just makes memory management much more secure, so we don't have stray particles that might eat up memory, because the Flow MPM solver is a grid-based solver. So now we have all these setups, and the most interesting part we are coming to now is our Flow solver or coupling physics solver. So we are using a multi-physics simulation here. So we have the Flow solver, which handles our sand simulation, but we also have the rigid body part, which is a bullet physics solver. So to handle that, we have an output in our solver that's called external solver, and that will trigger our rigid body dynamic solver. So whenever our sand simulation is done, it will call for the rigid body or any other solver we connect to that. And then this ensures that we have proper physics coupling. Let's have a look at the rigid body dynamics part, which takes care about creating our actual sand particles. Many things have to happen in here in this dynamic set. Keep in mind, we want to create the sand particles for our sand simulation. We want to have our rigid body dynamics happening, and we need to transfer materials later on as well. So the first setup here is our bullet physics. It's a standard bullet physics setup, and we are going to just concentrate on that at first. So let me just turn off the AND operator. What it does is we turn off all the right-hand part. So we just concentrate on our bullet physics setup. Let's have a look what the rigid body dynamics look like. Let me just switch to viewport and playback. So here we can see that's our rigid body dynamics. So we have the objects here. All the objects have their material. However, there is one special object we need special consideration later on. So all the other objects have standard materials without any textures. However, one object here has a texture, and we need to be careful about that. And the object is our pyramid. So let me just turn on the viewport display. As we can see here, we have this checkerboard on the pyramid. Let me just play that back so that you see what happens. So what we want to achieve is our sand particles should represent the surface color as well. So we want to, when we turn this into sand on contact, we want to make sure we get the correct colors of the surface as well on our particles. For the other objects, we don't care, because that's just plain colors or materials we have here. So I'm going to explain how we did that. But the most important part is the detecting which object is which. So the memory operator is very important for the object ID. That will store or transfer the object ID. That will allow us to detect later on which sand particle belongs to which object. So the bullet physics is a standard setup. We feed in the floor object, we feed in the group, we use the force group, which is with subgroups, so we get all the objects, sand and objects, individual objects in here. And we have our floor, where we use the high resolution bowl, which in the case of bullet physics doesn't really matter because it's so fast. So I don't care. I just picked the high resolution bowl for bullet physics. It's more important to make sure we use a low resolution for our sand simulation, as I explained before. So now let me reactivate our AND operator here and explain what it does and why we want to have the AND operator working. Let me just turn that on. So the AND operator does one important part. We have the collision particle output and we have the collision floor output. And what I'm doing with the logical AND is, whenever there's a collision and the collision is with the floor, I want to activate the creation of sand particles. So keep in mind, the collision output is usually any collision. So if object A with object B or object C, it will give an output there. So that's not enough of an information. I only want to filter out the collisions with the floor. So when an object collides with the floor, we are going to activate all the right-hand side of my setup here. So on the top, we create the particles, the sand particles. Then we grab our memory operator with the object ID, and we activate the expression, and then we kill the particle. So on contact with the floor, we start with our first step, creating the sand particles. So we turn our rigid body into a sand simulation. So what we're doing here is I'm not using the vertex particle. I'm using the simple deform not to deform the object. I just abuse it to create surface particles and volume particles, because it's the only operator we have where you have on the surface a raster option. So now we can create particles in a raster on the surface. And we have the same for the volume particles. So one operator gives us surface and volumetric particles, which allows us to play around a little bit with the volume amount and the surface amount. So we can close the surface really easy and make it appear as a solid object made out of particles. So we get the surface particles out there, connect the surface particles, the original particles, object ID. We grab the object ID at the same time when there's a collision happening. So when an object collides with the bowl, we grab the object ID. I want to know which object actually did collide, because I don't get the information out from bullet physics. It doesn't tell me which object did the collision. So I'm checking with the particle ID and the memory what object did collide, which object did collide. So that's what we did here with the memory operator. Remember, we store our Born ID. So we know exactly sphere is 0, pyramid is 1, sphere 001 is 2, and so on. So now we can tell which object did collide. That's important in a later step. We are going into the surface particles dynamic set in a second. And then we will explore why we need this information to do some more effects on these specific objects. Let me just go to the surface particle, and the setup is identical to the volume particles, so we will just work with the surface particles for now. So the first thing we get here is our transform. So I'll get the point in the position of our sand particle, and the position is supplied by our simple deform when it creates the surface particle. So when the surface particle is created, I just feed in the particle stream to the point input, and that automatically converts or gives the position of the particle to the transform node. And the transform node, I use this node here to allow for some turbulence or change in our cellular node that is connected to here. And the cellular node uses the object ID because I only want to work on the same object. So we could have thousands or millions of particles that belong to different objects. So I just want to make sure I'm working on the same object, and I create with a Voronoi structure a cluster. So I want to have some clusters clumping in the sand where we have some chunks of sand that are baked together. So this is where I create the cluster ID in the data channel for the sand particles. The next thing is I'll grab the sand particle, and with the original particle, I will do the transfer. So I'll grab the sand particle and the original particle. So what's happening here is I transfer the original material from our sphere, torus, and pyramid. I'll transfer the same material to the new sand particles. So that's a very helpful and efficient method to transfer the material to a newly created particle. And then I also want to make sure we set the object ID for the newly created sand particles. So all the new sand particles will also get the object ID of the object that created them. So now I know each particle belongs to a specific object. And at the very last step, I will just go ahead and create a standard shape. So that's basically the process how I create the sand particles for the MPM solver. I use the cellular to create, based on the position, a Voronoi structure to clump them together. I'll transfer the material and I'll assign a shape. So that's the whole setup we have here, where we create our sand particles and assign and transfer material properties. So there's not much else we need to do on the sand particle side. Let's move on to the next step. All we need to do is, or what's left to do is, we need to kill our original particle, the sphere or the torus or pyramid, on contact. And we are just doing that with a simple particle die. Make sure that in the hierarchy it's the last thing. We don't want to kill the particle first. And at the moment of impact, we kill this particle, the original particle. And all that is left then is our sand particles. So that's all we have to do now. Let's talk about materials now. You remember we have these plain materials, just colors, reflections, and metals. However, we have this one special object, our pyramid, that uses a checker. This checker texture, we would like to represent this checker texture in our sand particles. To do that, we are using a simple MEL script that does all the magic for us automatically. We feed in the objects in the same order we've picked them, sphere, pyramid, sphere, torus, and then we go over these objects and sand particles and grab the information we need. So the first thing we need is we need to get our node ID from the data channel. So our object ID is channel 1. So we grab from channel 1, we grab our object ID. I called it node ID here. So now we know which object it is. If it's 1, that's our pyramid, we want to use the closest point function. So we grab the closest point to the surface of this object of our pyramid, and then from this point we grab the color from the surface. So that's a shading effect. We really grab the color from the surface of the pyramid, and then we set this color in our data channel. And we set this in our data channels 0, that's the grain color. So now the sand particle has the color attached from the surface of the object. So these few lines of code just make all the magic to transfer the particle of the surface to the color of the surface to a particle. That's all what's happening here in the expression MEL script. So all the objects we are going through, when it's pyramid 001, that's our object 1, we assign the color to the sand particles. And then at the very last step, we need to assign a special material to the pyramid particles. So what we're doing here is only the pyramid particles will get a special material we want to have there. Remember, we transferred all the materials already. So all the plain materials like mirror, gold, and color are fine. We don't need to do anything special. However, for our pyramid, we need to be careful and do something special. The pyramid needs a special material so that we can grab the color from the particle itself. So when the particle is rendered, it needs to supply the color at that position in space for this particle. So what we do here to get this done is, as I mentioned, we transfer the particle color as I mentioned here. So now the particles have the color of the surface from the pyramid with this script. And then at the very end, I'm going to assign a new material just to the pyramid particles. And we do that with the A equals B. So when our particle, our sand particle that is newly born is 1, which is the pyramid, and here we have the born condition. So when a particle is born and it's our pyramid particle, I'll assign this special material. And I'll explain now which material we are using. We're using this color checker physical material. Let me just show you, and that's this material. So we assign this material, and we don't have a checker there. What we do is we have this TP data channel material that allows us to access the particles and channel information of the particles, or the content of the data channels in a particle. So I'll grab the sand particles and I'll grab the grain color data channel from this material. So I grab just the color and put it there. So now we should get the exact surface color we grabbed before. Now the color is part of the particle itself. So whenever this particle is shaded, it will ask for the color information in the data channel, and the shader will use this color. Assigning this special material is really important and makes sure that the specific sand particles will be colored accordingly to the surface color of the object, in this case of our pyramid. So let me just collapse all this, clean it up. Here we have all our setup, and let's have a look now how this works out. So let me just play back this simulation, and on impact we get the sand particles. However, we can't see right now in the viewport, do we get the checkerboard or not? Let me do something, a little trick for debugging if we actually transferred the color to the particles. Let me create a new dynamic set. Let me name this dynamic set debug. We want to debug the color we assigned in the data channel. So go here and I'll grab a viewport color node. And let me grab the sand particles, feed in the sand particles. And we want to enable the color data channel and feed it into the viewport color. The value is wrong. Sorry, that was my mistake. We want to set directly the color of the particles in the viewport. So now what we have is we grab the data channel grain color, and let me just step one more. And we get our checkerboard in here. All the other particles are black because we did not assign any color to them, because we don't need to. These are just plain color, either silver or gold or blue or whatever color. But the texture is transferred. Let me just play back the pyramid and we should see it much better. Probably having a black checkerboard is not the best in this situation. Let me just change the color a little bit. So let me just go to the original material of the pyramid. And then let me just change the black color out a little bit to something we can better see in the viewport with all the black particles. Let me play back again. And there we go. Here we have our pyramid with the colors. So now we achieved what we wanted. We can transfer the texture, the surface color of the texture from the object to our sand particles. So now I turned off the debug and we're back to our flow MPM display. And let me just show you what we do here. We have the cluster visualization turned on in our sand solver. So what we see, the colors, is our clusters or clumping of the sand particles. So that's about all we need to do here. Is we create these clusters with the cellular, with the Voronoi pattern, and assign the cluster ID. So all particles with the same ID or same color will be clumped together in our sand MPM solver. By the way, we have other tutorials that go really deep into the new MPM solver, especially sand. If you want to learn that, check out these tutorials as well. Thank you for watching this tutorial, and I hope to see you again. Goodbye.